Okay, folks, we can get going. I had just a couple of administrative things to talk through before we get into the content. The first is, I put a thing on Ed yesterday. I posted the Lab 1 report assignment on Canvas. I'll just remind you that these are group assignments, so I only need one lab report per group. And on Canvas, we did make lab groups based on groups in lab. Now that said, there's like 120 people in this class, and almost certainly we misassigned somebody to a group. So please double check, and if you notice that we put you in the wrong group or that something's wrong, just let us know. I think we got them mostly right, but I'm sure there's mistakes in there, so just let me know if you find any. And I promised too that I would post some examples of lab reports from previous semesters that were pretty good, and I'll do that today. I'll post an announcement on Ed once I've done that. I found some good ones and I have them downloaded. I just need to put them up on the website. Any questions from anyone about any of that stuff? Okay. I've been getting one question a few times in lab, and before I get into today's stuff, let's just, I want to just address it. The question I've been getting is in connection with the VGA example that you're getting set up for Lab 2, which we started taking a look at a little bit last time. Let's see. Let's look at this one here. The question that I've been receiving is, folks are wiring up the VGA screen to the various GPIOs of the RP2040, and what they've noticed is one of the GPIOs goes to H-sync, another to V-sync, one to blue, one to red, one to ground, and two go to green. Two go to green through two different value resistors. And the question that I've been getting is, which one connects to the VGA cord itself? The answer is both of them. Both of them go into the VGA screen. What we're setting up here is a very simple little resistor DAC. So we have, the reason that we only have 4 bits of color, 1 bit of red, 1 bit of blue, 2 bits of green, is because we only have 256 kilobytes of RAM on the RP2040. We're driving a 640 by 480 VGA screen. So 640 by 480 is 307,200 pixels. So you can ask yourself, with 256 kilobytes of RAM and 307,200 pixels, how many bits do you have to store for each pixel before you run out of memory? And the answer is 4. You can get away with 4 bits per pixel. And so what this means is we have 1 bit for green. That means green is either on or off. 1 bit for red. Red is either on or off. I'm sorry, 1 bit for blue, 1 bit for red, 2 bits for green. That means green can be off. It can be sort of a little bit on. It can be 3/4 on, or it can be all the way on. We have different levels of green that we can use. If you have 4 bits to spend on color, why spend the extra bit on green? Why would we spend it on green? Anybody know? We wouldn't have to, right? We could have spent the extra bit on red or on blue, but we chose to spend it on green. Yeah. Yes, your eyes are most sensitive and best at differentiating shades of green. And so with 4-bit color, you can generate a 16-color color palette. If you spend your extra bit on green, those colors are maximally distinguishable to our eyes. Why do we see the best in green? Yes, so part of your question?
Also see predators in green, isn't it an evolutionary thing?
So I'm not speaking as an expert here, and if I say anything wrong, Bruce, correct me, but I think that there's sort of 2 answers to this question. One is there's probably some evolutionary aspects to this, where it probably was to our advantage to be able to distinguish, say, ripeness of fruits and so forth, and that green distinguishing ability is valuable for that. The other reason for this probably is the sun is a blackbody radiator. So, it has a blackbody radiation curve. That means it's radiating on all wavelengths, electromagnetic energy on all wavelengths. Right at the top of that, where the most power is is green. So it kind of makes sense for that, if that's our sun and it's radiating the most power at green, kind of makes sense that our visual instruments would evolve such to see at that particular wavelength. So that's why we chose an extra bit for green. Here's a follow-up question. Let's say we had to get rid of a bit. What color do you throw away? What color do you have the least sensitivity in? Do you know? Turns out it's blue. So if you have an extra bit to spend on a color, you spend it on green. If you have to sacrifice a bit of color, you sacrifice it on blue, because we're least good at distinguishing blue shades. It's kind of interesting. So there's that. By the way, just as a quick aside, this is not true, of course, for all organisms. And so, for example, deer lack a red color channel. And so if it has ever puzzled you, how the hell is it possible for a tiger to sneak up on a deer? The thing is bright, glaring orange, right? How does it sneak up on deer? The reason that it can sneak up on deer is that the animals that it's actually hunting and is trying to camouflage itself from lack a red color channel. And so from the visual perspective of the deer, the tiger and the surrounding foliage are very, very close to the same color. And so it's evolved to hide from the animal that it's trying to hide from. It doesn't care to hide from us necessarily, right? So that's why it can get away with being bright orange. That's why also hunters can wear bright orange vests and go hunting for deer, and the deer they remain camouflaged from those deer because the deer aren't sensitive to that color channel. So if we were building a visual interface for deer, right, we would throw out reds. Reds get us nothing, but we're building it for humans. Any questions about this stuff? We're going to talk more about the VGA driver and the VGA code in more detail in a subsequent lecture. Yeah?
So when you say 1 bit each for red, blue, green, and green, does that mean that there's just 16 possible colors?
16 possible colors, and that's it. Yeah, Bruce? Oh, yeah, let me see. Where can I find that? That would be VGA.h. Yeah, so here's the names of the colors, and I can track down a web page that shows each of these colors, but this is the colors that you get. Let me see if I can find that quick. It's going to be down here at one of these links. 16 color. Here are the colors you can make. As someone who's not like a color theory specialist, it is counterintuitive to me that with only one extra bit of green, you get this richness, right? That's a whole lot of colors. Okay, any other questions? So, you know, it's not enough to like beautifully emulate the Mona Lisa, but it's enough for a really nice video game interface or something like that, right? Okay. Any questions about setting up Lab 2 or anything before I move on to some additional Lab 2 content? So as I mentioned last time, the exercise in Lab 2 is, in the first week, is to integrate 2 demos. One of those demos is the VGA animation code that we spent a little bit of time looking at last time and we're going to revisit. The other demo that you're integrating is a DMA example. And this leads to, we need to have a conversation about what DMA is and how it works. Let me just say, I hope that you take a lot from this class. One of the things that I really hope you gain an appreciation for in this class is how powerful DMA channels are on these microcontrollers. Man, if there is a peripheral to gain an understanding for and to gain an appreciation for, it's these. They're really powerful. I'm going to do my best to try to illustrate why it's such a good idea to gain an understanding for how these things work and how to use them. Let me start by just reminding you at a high level what these things are. This is that block diagram of the internal systems in the RP2040 from the data sheet that we looked at a while ago. And I just wanted to remind you that the DMA channels here, they connect to the bus in much the same way that the 2 processors do. That is to say that the DMA channels, like the processors, are bus masters. They can issue bus transactions. They can send stuff through this bus to the peripherals. They can send stuff through this bus to the memory, right? They could send stuff from memory to memory and so forth. So the idea here is that each of these DMA channels is essentially a very, very simple coprocessor. It is a system that lives outside of our two processors. It does stuff independently of those processors. It can, of course, communicate with them, right? But they exist totally independently. And all that these simple coprocessors can do is move data from one place in memory to another place in memory. The power of this on these microcontroller devices is all of our peripherals, our SPI channels, our PWM channels, our UARTs, our I2C channels, the ADC, all that stuff, and of course our memory, all of that stuff is memory mapped. So that means for every control register of every one of these peripherals, every receive buffer lives at an address in memory that you can open up the data sheet and go find. So that means that your DMA channels can move totally separately from the CPU with no CPU interaction whatsoever and consuming no CPU time. They can move information from, say, a peripheral to memory. An example of that sort of thing might be you could set up the say the ADC. You could set the ADC up such that it's just gathering samples at some rate on its own. And every time a sample appears in the ADC FIFO, you could set up a DMA channel to whisk that off to some array in memory. And once you've filled up that array, throw an interrupt to the processor to just let it know, hey, your data's there to go process. But while you're filling up that array, the CPU is spending no time actually interacting with the ADC. That's all just happening in the background. You can send information from memory to a peripheral. I'm going to demonstrate this today. But the example of this that I'm going to demonstrate today is, for instance, you could store audio information in SRAM and set up a DMA channel that at audio rate goes into SRAM, gathers the next audio sample, and whisks it off to the SPI transmit buffer, where the SPI channel just sends it off to, say, a DAC hooked up to that SPI channel, so that you generate audio with 0 CPU time. This is very different from Lab 1. In Lab 1, we were synthesizing audio in an interrupt service routine, right? And you all actually timed how much time you were spending in the interrupt service routine. The exercise there is to keep that time as low as you can, but 50,000 times a second, you're leaving your application code to go into this interrupt and do something for some amount of time and then come back. And incidentally, our measurement of the time in our interrupts there in Lab 1 is a little bit of an underestimate, because what we're not accounting for there is the overhead associated with actually getting into the interrupt, and then the additional overhead associated with getting out, right? So you're spending time going up there to do that audio synthesis. In Lab 2, you want to spend 100% of your CPU time doing animation. That's the whole exercise. So you don't want to waste those cycles interrupting to synthesize audio. With a DMA channel, you can have the audio production occurring just in the background. Again, no CPU interaction. All the CPU has to say is go make a sound, and then the sound comes out. You can, of course, move information from memory to memory. You could think of this as a very fast behind-the-scenes memcopy, where you say, please take the contents of this array, for instance, and put it over here into this array, and that would all occur behind the scenes. And you can move memory from a peripheral to a peripheral. I'll pull up a demo of this today as well, but you could, for instance, gather information from the ADC and whisk it off to the SPI transmit buffer connected to a DAC. And if you hook up a microphone to that ADC, you could talk into the microphone and your voice would come out of a speaker. And that would be occurring with no CPU time being consumed at all. Now, you could imagine this basic capability that I'm describing, the capability to move information from one place in memory to another place in memory. There's a few degrees of freedom there that we have to specify. In particular, we of course have to specify the source and destination memory addresses. Where do you want to move the data from, and where do you want to move it to? And there's some little details associated with that as well. So if you want to, say, move a big array of data to the SPI transmit buffer to send off to a speaker, you can configure the DMA channel with a starting source address and then tell it, every time you send a transaction, step forward by one address so that you move through the array. So you can set up, and you can do the same with the destination as well, of course, right? So you can have that walk through memory if you want to. You have to specify the transfer size. Do you want to move data 8 bits at a time, or 16 bits at a time, or 32 bits at a time? You specify the number of transfers. How many transfers do you want for the DMA channel to do before it stops? You have to specify that. And then you also have to specify the conditions under which the DMA channel starts and the conditions under which each transaction occurs. So do you want for the DMA channel to just open the tap and move data as fast as it can from one place in memory to another place in memory? Or instead, do you want to pace those transactions so that they only appear at, say, the SPI transmit buffer at 50 kilohertz? And each of these peripherals has what the data sheet calls a, all caps DREQ, a data request signal. So each of these peripherals can generate a signal to the DMA channels to say, do a transaction. So you could set up a DMA channel to say, oh, you know, what would be a good example of this? Move data from the ADC to memory, and you could specify that it should only move data when it receives a data request signal from the ADC. So it will only move memory when the ADC says, I just put something in my FIFO, please come get it. So the power of this is it's totally separate from the CPU, and each of these DMA channels can perform one read access and one write access up to 32 bits every clock cycle. You have 12 of these. The amount of throughput of data that you can achieve with these DMA channels with no CPU interaction is astounding. Each of these can, of course, interact with the PIOs as well, right? So you can get, with the PIOs and the DMA channels, you can build rather complex applications that don't involve your processor at all. The VGA driver is an example of this, which we'll talk about in a subsequent lecture. There's 12 of these, and you can do some twisted stuff too. I mentioned that all these peripherals are memory mapped. That includes the DMA channels. So the control registers of the DMA channels are also memory mapped. And so what that means is you could set up DMA channel A to write to DMA channel B's control registers. And this particular platform allows for what they call DMA channel chaining. So you can say, please start channel B please start DMA channel B as soon as DMA channel A has finished. So DMA channel A finishing will trigger this one to start. And then you could set it up trigger in the opposite direction as well, so they ping pong forever back and forth. But you could write to the control registers of other DMA channels, and you can do some little tricks on this system as well. Like the DMA channels can do things like bit reversals in flight, if you want to. So you can bit reverse the data as you're moving it. It has an associated sniffer register, which allows for you to accumulate a sum of the data that you're moving as you're moving it for computing something like a checksum, for instance. So by having DMA channels trigger other DMA channels and write to the control registers of other DMA channels, it can get really twisted and really complicated. Moving information, doing very slight modification of the information in flight. Is this starting to sound a little bit Turing machine-y to anyone? Turns out that these DMA channels are in fact Turing complete. And as proof of that, there's a delightful web page linked up here. This is a Bruce project. Let me just point you to it. You can go read about it. Why aren't you responding? Hello. Let's see. DMA. Hold on. My web page isn't responding. There we go. Down here. DMA computing machine. A full general processor implemented only in DMA channels. So I don't know, you can incorporate this in your final project if you wanted to. So they're extremely powerful, and it's one of these things that's hard to articulate just in the abstract here. It really becomes apparent when we start looking at some demo code. So let's do that. The particular example that I'd like to take a look at is the audio DMA demo. This is one of the two demos that you'll be integrating in Lab 1. And I want to just let's take a moment first to just talk about what this is doing. You may remember from lecture 2 or 3, one of the first examples that we looked up was a timer interrupt direct digital synthesis example that was just generating a tone. And much like that example, all that this one is doing is generating a pure tone. Okay? So the output, the behavior of this program is identical to that timer interrupt example, but it's different in a really interesting way. If we look at this, some of this looks familiar. Much like before, we see a sign table that we're working on building here. There's a subsequent table here called DAC data that we'll look at in just a moment. There's some stuff here for the SPI channel that looks very familiar. Okay, and then we have main. No interrupt service routine here. Unlike the timer interrupt example, no interrupt service routine, there's just main. What's main do? Initialize standard I/O, initialize the SPI channel, set up our GPIOs for the SPI channel. It populates the sign table and populates this DAC data table. I'll come back to that in just a moment, but it populates 2 tables. This is setting up our DMA channel. We're going to talk through this in detail, but let's just look at the structure first of all. Set up our 2 DMA channels and start one, and then look. There's no while one loop. There's no adding of any threads. We exit main. What happens usually when you exit main on a microcontroller? Nothing. Everything. There's no operating system here. You have nowhere to go. So typically when you exit main, that's it. The system's just dead, right? It's not doing anything. But this system, that's producing a nice pure sine wave. The speakers are terrible. The sine wave is actually very nice. It's producing a nice pure sine wave. That's a rather complicated task, right? With precisely 0 CPU instructions occurring. So I mentioned at the very beginning of this class that one of the things that this class is about is hardware-software co-design, and that the hardware that I'm talking about in this class includes the stuff that you breadboard next to the microcontroller, but is not limited to that. The hardware in this class with which you're designing also includes all of the internal hardware peripherals. And I mentioned too that the software that you write in this class may be different than software that you're used to writing for other kinds of computers, in that it not only includes instructions for a processor to execute, it also includes configuration and control commands for these external hardware peripherals. And this code is proof that your programs do not necessarily include instructions to these processors. At the beginning of main here, there are some instructions to our processor, right? I mean, it's doing some stuff. This, for instance, is, the processor's doing some stuff. But all we're doing here is setting up those internal hardware peripherals. And then once the application's actually set up, there's precisely 0 code executing on the processors. Precisely 0. What that means is we could add to this an arbitrarily complex program that runs on the ARM processors, a ridiculously complicated animation loop or something. And it has no idea that sound is being produced. They're totally independent processes. So a good practical example of this might be, let's say for your final project, you want to build a computationally intensive video game. One that involves lots of interactions and graphics and so forth, for which you would like to spend as much time as you can in a pretty tight animation loop. But video games need background music. It's boring to play a video game without background music. With DMA channels, you could figure out the background music that you want, put all of that in flash memory, label it const. Your code's never going to manipulate it, so it goes into flash memory, and set up a DMA channel that at audio rate just walks through that array, sending it off to the speakers, and when it gets to the end, it triggers a subsequent DMA channel that resets the read pointer of the first one, and it walks through it again. And the consequence would be you'd be producing nice background music for your video game and sacrificing nothing with regard to the amount of CPU time that you can spend doing video game stuff. Isn't that cool? So how does this actually work? So in this particular example, like I said, most of this stuff is familiar. There's just a couple of new things. One of the new things that I pointed to was we have our sine table here, which is familiar to all of you at this point. And now we have this DAC data table of the same size. You'll notice that this DAC data table is populated in the same for loop as the sine table, and it contains exactly the same information as the sine table, but prepended to each sine amplitude, we have those configuration and control bits. So you may remember from lab 1, every time we did an SPI transaction, we took our 12 bits of data that we wanted to send to the DAC. The top 4 of the 16 bits that we sent to the DAC were configuration and control. Do I want this to come out of channel A or channel B, our gain selection bit, our shutdown bit? And we would mask it on to make the 16 bits and then send that over. In this case, we prepend every element of this table with that configuration and control bit so that the DMA channel can just go grab whatever at that index and send it off. And it's already formatted properly for the device that we're trying to communicate with. But that's not such a sacrifice, right? And that's easy enough. And then we set up 2 DMA channels. One shuffles data off to the SPI transmit buffer. The other resets the first one. So let's look first at the one that sends data off to the transmit buffer. And what we'll see is that basically we're specifying all those degrees of freedom that I was speaking to a little bit earlier on the slide. So when we want to set up a DMA channel, typically you'll start by creating a DMA channel config object. This is a C SDK object that we use to configure DMA channels. We're calling this one C2, or channel 2. And to begin, we set it equal to its default conditions. We could go look at what those default conditions is, but there's some default value for, the 8-bit transfers versus 16-bit transfers versus 32-bit transfers. All those degrees of freedom have default values. And we're saying to start, let's just start with all the default values, then we'll change them as we need to. The next thing we do is we're saying, for this particular DMA channel, I would like to do 16-bit transfers. Why 16-bit transfers? Because our SPI expects 16-bit transactions. And so we want to dump 16-bit data into the SPI transmit buffer. So we're going to do 16-bit transfers. We're setting our read increment to true. Remember that I said we can configure these DMA channels such that we specify a starting read address, and then we tell it, every time you do a transaction, walk forward. So what this means is after each of its transactions, it will step forward in memory 16 bits to the next element of the array, and it'll walk the whole way down the array. We set our write increment to false because we do not want for our destination address to change. Our destination address is always the SPI transmit buffer. That's the same place in memory all the time. We dump data there, the SPI peripheral whisks it off, and then we dump more data in the same place. So that doesn't move, but our read address does move. We want to pace this DMA channel such that it is sending data to the DAC at audio rate. Each of these DMA channels has its own timer. And we can configure that timer such that it overflows at whatever rate we would like. And every time it overflows, we do a new transaction. Now, this is a little bit cryptic. And in fact, I wrote this example about a year ago. And I think since then, they've added some more readable features to the SDK. And so I'll update this so it's a little bit more readable. But in short, all that this is doing is specifying the configuration for that timer. This particular SDK function, let's see, what we are saying is, please configure the timer such that it overflows at 44 kilohertz. And what these numbers actually mean is, the DMA timer here is set to the system clock rate, 125 megahertz, times the second argument divided by the third argument. If you do the math here, hex 17 divided by 65,000, whatever, and multiply that by 125,000, you end up with a number that's pretty darn close to 44 kilohertz, which is, a reasonable audio synthesis rate. And then here, we're specifying that we would like this too. I'm sorry, there's a more readable SDK update here. But this is specifying that we would like to pace our transactions using that timer. Hex 3B stands for that timer there. Like I said, there's a more readable name for this now, and I'll update that before next time. Okay, so all we're doing is configuring the DMA timer and then telling this DMA channel, hey, pace your transactions based on that timer, right? We set it up to 44 kilohertz, and then we're saying, do your transactions at the rate that that timer's ticking. And then we're doing this chain 2. What this says is every time you finish with your transactions, automatically trigger this channel to run. And we'll look at this channel in just a moment. But you'll notice, incidentally, that this channel chains back to the first one. So these two are going to ping pong forever. Okay. And then we do our configuration. So this DMA channel configure function from the CSDK as arguments. It takes the name of the channel we're configuring. We happen to just call this one data channel. A pointer to the DMA configuration object that we just created. It takes the write address. Where do we want for the DMA channel to move this data to? And what we've specified here is that we would like for it to move the data to the DR field of the SPI struct. And you may remember from one of the earlier lectures that at the bottom of this SDK is all the registers. There's some human readable name next to an address, right, that specifies every register's address in this whole system. One level of abstraction up in the SDK, all those registers are organized into structs. And so all that we're doing is accessing the data register of the SPI channel. We're doing it through this field because it's a little bit more readable. I mentioned that most of your programming in this class would take place at the hardware API level of abstraction of the SDK, but that you would occasionally pop down to the structs when you're setting up DMA channels, right? And here's an example of that. We specified the initial read address. The initial read address that we've specified is DAC data. DAC data is just the name of this array. I'll just remind you that in C, the name of an array is a pointer to the 0th index of that array. So DAC data is equivalent to ampersand DAC data bracket 0. Address of 0th index and DAC data are the same. So this is a pointer to the 0th index of that array. We specified the number of transfers that we would like for this to do. We've specified that as the size of our table. Please walk through the whole array. And then this last false argument, if that were true, it would start the DMA channel as soon as it hit this configuration line. We're not doing that. We're going to start it with a subsequent CSDK function call. Okay. So we've configured this DMA channel for 16-bit transactions. It will move data from that DAC data array to the SPI transmit buffer. It will increment its read pointer each time it does it. It will do 256 of those transactions, and it will pace those transactions according to the timer that we just configured. Once it finishes, because of this chain, it automatically triggers this DMA channel to run. We happen to call this DMA channel the control channel. This one we've configured to 32-bit transactions. We're doing 32-bit transactions here because we're going to write to one of the control registers of the other channel. These are 32-bit registers. We're going to do a 32-bit transaction. Both our read increment and write increment are false because we do not want either our read address nor our destination address to ever change. And we chain to the other one. As soon as this one's done, it starts up the other one. So what's this one doing? Well, as before, this is the channel we're configuring. We called this one control channel instead of data channel. This is the channel configuration object for this channel. The other one was C2. This one we just happened to name C. The write address for this channel, where it's moving data to, is the read address field of the DMA. Okay. The DMA struct contains configuration and control registers for all 12 DMA channels, right? Organized into an array effectively. So this is saying, please go to the data channel, and we're going to write to the read address register of that particular DMA channel. right? So we're writing to its read address. Once it's finished its transaction, its read address is at the end of that array, right? We have to put it back. Where are we reading from? What data are we going to move to that destination address? We give it the address of this variable address pointer. What's address pointer? Address pointer is just a pointer to the address of the 0th index of that array. So that register that we're writing to, it wants an address there. Here's the address that we want to put there, the address of the 0th index of DAC data. So we're rewriting the control register of that first channel. After it's finished, that register, its read address, is all the way up at the end of the array. We're writing it so that it's back at the beginning. In contrast to the other channel that's doing 256 transfers, the size of that array, we're just going to do one transfer here. We don't start this one immediately either. Okay? Once this transfer occurs, right, we will reset the read address of that other channel and trigger it, and it will just go through and do it again. And so these two are going to ping pong forever. The data channel moves through that signed table array and sends it off to the speaker, triggers the other one that puts the pointer back at the beginning, and then it does it again. And then how do we actually start this whole process? We start it by triggering the control channel to start. So in other words, that DMA channel that we were just looking at, our software says start that channel. So that will write the read address of the data channel and trigger it to start. The data channel moves through that array and sends it off to the speaker. And these two will then ping pong forever. Yeah?
Would there be any difference of, instead of using that line that you highlighted, setting one of the channel configs to true?
No, there would be no difference.
Okay.
Yeah. In this case, there would be no difference. My convention is generally to start it in an explicit line because it helps with my debugging, I think. I like to say, here is exactly where it's starting, and then I know that, those are the initial conditions. Yeah. Yes? Is
it possible to have two DMA channels running at the same time?
Mm-hmm. It's possible to have 12 running at the same time. Other questions about this? In Lab 2, you're going to be modifying this gently. In Lab 2, we don't want a persistent sine wave. What we want instead is a little thunk sound every time a ball strikes a peg. And so the way that you will generate that is when you detect that a ball has hit a new peg, you'll have a line that looks kind of like this that tells the DMA channel generate a thunk. How do you make a thunk? Well, in Lab 1, remember that we ramped the swoop and the chirp, each of the bird songs. We ramped them on, sustained them, and ramped them off. And you may remember that the reason that we ramped them is that if you don't ramp the sound on, what you end up hearing is a click or kind of a pop sort of sound. The reason that you hear that, as I've mentioned a couple times, is one way of thinking about this is that's a step function. The Taylor series of a step function includes a whole bunch of sine waves, and you hear all those sine waves. The more physical version of that explanation is when you send a step function, that membrane in the speaker pops and wiggles. And those pops and wiggles has high frequency content that all comes out at once. Sounds kind of like a click or a thunk or something. In Lab 1, that's a bug. But a general principle here is you can never do anything wrong when you're programming these things. It's just everything that you do has consequences. And so you need to understand the consequences of what you're doing. And so it would be incorrect to say it's wrong to go full amplitude on an output to the speaker all the time, because maybe sometimes you want those artifacts. To my ear, those clicky poppy artifacts sound a hell of a lot like a ball bouncing off of a hard surface. And so the way that we'll generate a thunk is you will not ramp up the sine wave. You'll just send one period of a sine wave at full amplitude out to the speaker. What you will hear will not just be that sine wave. It will include all of the audio artifacts associated with doing that, which in this case is a feature. So you just have to understand the consequences of what you're doing. Years ago, for like a month, I was taking flying lessons, then it got way too expensive, and so I stopped. But I had this idea got into my head from this flight instructor, because I had read somewhere you should never cross-control an aircraft. That is to say, you should never go rudder this way, aileron this way. And I mentioned this while we were in flight, and he took offense to it. He was like, of course you can do that. The consequence of doing that is that your airplane loses a lot of altitude really quickly, which, if you don't want to do that, is a really bad thing to do. But he explained that there's a lot of situations in which you want for your airplane to lose a lot of altitude really quickly because of something happening. And in that situation, it's really good to understand that this control input has this consequence. So this is kind of a very low stakes example of this. The consequence of the control input of a full amplitude sine wave is click. If you understand that consequence, you can use it as a feature. Okay. I thought maybe we'd glance at one more DMA example that's a little bit tangentially related here, but I'd like to hit this a few times to try to illustrate what's so interesting about these. So let's see. I'm going to pull up another example. Let's do, I forget what I called it. Voice over radio. Let's look at this one. This example, which I do not have the hardware here to demonstrate, but what this example does is it too exits main. Okay, so there's no code executing on this processor once we've gotten to this line of code. But it sets up a different set of peripherals for interaction with the DMA channels. Previous example we were looking at, the peripherals that we set up, really just the SPI channel, and we put some data in memory. And those were the two things we got talking to each other. This example sets up the ADC, and it sets up a PWM channel, and then uses DMA channels to facilitate communication between those two peripherals. And in particular, what it's doing is we're setting up the ADC to automatically sample at 10 kilohertz. We're going to have a whole lecture about the ADC, so for the moment I'm going to wave my hands out a little bit, but like the DMA channels, the ADC has its own clock that we can set up, and we can tell the ADC, hey, every time this clock ticks, we get to configure the tick rate, gather a sample, put it in your FIFO. And so we set up the ADC to automatically gather samples and drop those samples in its FIFO at 10 kilohertz. And then we set up a DMA channel to grab data from that FIFO every time it appears, as signaled by the ADC through one of those data request lines. So every time a data appears in the FIFO, a DMA channel will grab it and plunk it into an array of memory. It will then trigger a subsequent DMA channel that goes in, grabs it out of that place in memory, and moves it to the control register of a PWM channel that sets the duty cycle of the PWM channel. And so when we configure the PWM down here, we set up its period. We set up its period somewhere here. By way of these lines here, which again, I'm waving my hands out a little bit and I apologize. We will revisit it, but suffice it to say for the moment that we've set up the period of the PWM channel to be an AM radio frequency. It's like 900 megahertz or something like that. And then we are using the samples from the ADC to set the duty cycle of that PWM channel automatically, behind the scenes with no CPU interaction. The consequence of this is you pull up the PWM channel on the oscilloscope and you talk into the microphone, and the frequency stays the same, but the duty cycle wiggles back and forth based on what you're saying. And you may remember from one of your calc classes that if you compute the Taylor expansion of a square wave, one of the first terms in that Taylor expansion is a sine wave that is of an amplitude that depends on the duty cycle of the square wave. Taylor series are real. And so the consequence of adjusting this duty cycle of the PWM is we can tune an AM radio to the frequency associated with the first term in that Taylor series expansion, that first sine wave in the Taylor series expansion, And as it wiggles back and forth, the amplitude of that sine wave wiggles up and down in an exactly correctly for AM radio modulation. So the consequence is you turn on a PWM channel, stick a little wire out of that pin, that becomes your antenna, tune your AM radio across the lab to the correct frequency and talk into a microphone, and your voice comes out the AM radio. This isn't technically legal, but it's really low power. But again, so that's a lot of complication. That involves what? ADC, PWM, we're interacting with memory a little bit. We have strict timing requirements to which we're adhering. It's doing all of this with no CPU running at all. The CPUs aren't on. So these DMA channels, if we just glance at them very quickly, the first one here is doing 8-bit transactions. We have the ADC configured for 8-bit sampling. 8-bit transactions, no read increment, no write increment. It is pacing its transactions using the ADC. Every time the ADC says there's a sample ready, it will go get it. We've chained it to the control channel. And what's this one doing? This one is just moving data to this array in memory. We could incidentally have moved it directly to the control registers. I think I was just moving it through memory so I could observe it, if I remember correctly. Okay, so in this case, we're moving it to memory. We're moving it from the ADC FIFO, doing one transfer. So every time data appears in the FIFO, go put it at that place in memory. This other DMA channel, which then immediately gets triggered, does a 32-bit transaction. It's a 32-bit control register. 32-bit transaction. It moves data from that place in memory where we just put the ADC sample, and it moves it to the duty cycle. It's the counter compare register, which effectively sets the duty cycle. It moves it to the duty cycle register of the PWM channel that's running. So that every time new data appears in that FIFO, it gets whisked off to the duty cycle control register, and the duty cycle adjusts. And then as before, we just start one of these, and it will start ping-ponging back and forth. We start the ADC, so that it just starts automatically sampling. And then this whole rather complicated application is running with no CPU running at all. Again, what that means is you could put an arbitrarily complex application on your processors, and that application doesn't even know that this other process is occurring, so long as you're not trying to use any of the hardware resources that this is using, right? They're wholly independent. So we're going to spend a little bit more time talking about this. I wanted to introduce DMA today. You'll get some experience with it in lab to generate these sound effects. And then we will also talk about it in the context of the VGA driver. VGA driver is something that's provided to you. You won't really have to modify it. You'll have to modify it a little bit if you want to overclock the processor, which all of you are going to want to do. You have to very gently modify it. But I want to spend some time talking through how that works, right? Because anytime something is abstracted away, I want you to understand what's abstracted away. And in the context of that conversation, we're going to talk more about DMA. Okay. Any questions? Yeah. Is
there a reason you chose 8 bits for the ADC?
Chose 8 bits for the ADC. It's a 12-bit ADC. The effective number of bits is 8.7. And so that means after you get to bit 8, it's mostly just noise. You have to imagine in these systems, that analog circuitry exists right next to the whole rest of the processor. There's gates flipping, there's current moving around. That's generating fields and noise and so forth. And so to ask for more than 8 bits out of a little ADC inside of a microcontroller would be asking a lot. But if we limit ourselves to 8 bits, that's pretty solid. There's not much noise there being introduced by the processor itself. We could, of course, introduce noise depending on what we build around it, right? But our effective number of bits is 8.7. Any other questions about this? Okay, sounds good. I'll be in lab this afternoon. I'll see many of you then, and I'll see the rest of you on Friday.